So in this section, we're going to start off with a variation of a formula we saw previously. And the point of this section is thinking about the multiplication rule that works generally. If you remember before, maybe we'll write in the top margin here a reminder. We had if the events are independent, then the probability of A and B can be found by simply multiplying the two probabilities together. But we said that's only true if the events are independent. Many scenarios are going to be covered where they're not independent. Think of our home team advantage across different sports, where we need a rule that will work more generally. So we can think about this a couple of ways. First, remember the conditional probability rule we had a moment ago. Probability of A given B is the probability of both divided by the given information. Now, our goal here, we're writing a rule that represents the probability of both, or the and. So I could do one simple step of algebra to solve for the and. I could multiply both sides times probability of B, and I would get something like this. Probability of A and B is probability of A given B times probability of B. So now I've just simply rearranged the formula to have an and probability that works anytime. So same thing, let's write our formula down here, and I'm going to write it a little bit different than the way I just derived it a moment ago, but just to help you think of it in another way. So probability of A and B is, you might want to think about it this way to start off with: A times B, and I'm leaving those spaces on purpose. So you might think of it as A times B to start with. Then you must go back in and write a given or a conditional statement on one of the two terms, depending on what you know in the problem. So for example, I might have A given B. I might put the conditional information on this first term, or maybe I'll have probability of A times probability of B given A. So again, start off with A times B, and then go back in and add a conditional or a given on one of the two terms, depending on what you know from the problem. So let me highlight this set of formulas for you. And let's do a couple of examples to show you what we mean. So let's start off with a more straightforward one here first. So suppose we're going to draw two cards from a deck, and it doesn't say it explicitly here, but what I mean is without replacement. So once we take a card out, we're not going to put it back in. And we want to know the probability of getting a heart on the first draw and a heart on the second draw. So I'll call it heart 1 and heart 2. So if we want to think about our new rule for multiplication, we might start off thinking it's heart 1 times probability of heart 2, and I'm leaving these little spaces on purpose so we can go back and add a given on one of those. So in this particular setting, which one would it make more sense to do? Heart 1 given that we draw a heart on the second, or probability of getting a heart on the second given we drew a heart on the first? Right, the second one. Probability of getting a heart on the second draw given what just happened on the first draw. We can't talk about the probability of the first draw given the second when the second hasn't happened yet. And now, if you know anything about cards, getting hearts, there's 13 out of 52 hearts. And so 13 out of the 52 cards, it's my chance of getting hearts on the first draw. And if I draw a heart on the first draw, my chance of drawing hearts on the second, well, now there's only 12 hearts left. And I've also drawn one card, so there's only 51 cards left in the deck now. And if you want to work that out further, be my guest, but leaving it in this format is also fine. All right, Let's try another one. This is going to look familiar. We know that 71% had student loan debt, so let's write all our information down. Probability of debt is 0.71. 16% attend private nonprofit. So we'll say probability private nonprofit is 0.16. Of those who attended private nonprofit, there's kind of a key phrase here. We're not talking about everybody now. We've narrowed it down to just that small group of students who attend private nonprofit. So that should be a big flag in your mind that we need this given notation. So private nonprofit, of that subgroup, 75% have debt. So probability of debt for the private nonprofit group is 0.75. So a little bit higher than just student loan debt in general, which makes sense. Probably those private schools are a bit more expensive. So our question is, what's the probability a randomly selected person goes to private nonprofit and has student loan debt? So take a second and write the question down in probability notation. And then hopefully you have something like this, private nonprofit and debt. That's our question of interest here. And using our multiplication rule, we're not just going to do debt times private nonprofit. We need to use one that works all the time because debt times private nonprofit is only for when they're independent. So we're going to do probability of debt. I'm going to start off that way, times probability of private nonprofit. Then I need to go back and add a given on one of these terms because they're not necessarily independent. So I'm going to choose what I add the given to based on my information. So I know debt given private nonprofit. So that term is going to get the given information. If I had given debt over here, I'd be scratching my head a bit. I wouldn't have a value for that. I couldn't plug in a number. So I'm not going to use that. Now we're good to go. Just plug in our values. Debt given private nonprofit, 0.75. Private nonprofit was 0.16. And that should give us 12% or 0.12. So again, maybe an easy way to think about it, multiply the two together and then go back in and add the given information. All right, last bit of new information for this section on probability is this idea of independence. So we want to test if events are independent. We've talked about it before, and we have some intuition that sure, maybe that's some things like rolling a die, tossing a coin. One outcome doesn't influence the next. But other situations, it might not be as clear, and we need to have a formal test. So we have options here. I'm going to write down 3 equations, and we're going to see if they're true. Test the left and right sides. If they give us the same number, then they're independent. If the left and right sides are not the same, then they are dependent. So here's our options. The first one, we already know this, A and B. So I might calculate A and B generally. And then C, is it the same thing as probability of A times probability of B? So we'll calculate left and right separately and see if they equal one another. If they do, independent. If not, dependent. The next 2 are basically the same formula. I might check A given B. Now, if A is not influenced at all by B, then A given B is going to be the same thing as A. It's like saying that given or extra information about B makes no difference at all, doesn't influence anything. So A given B is the same thing as A. And then the third option, as I mentioned, is essentially the same as the second. Switch it around, B given A. If A and B don't influence each other, then that given information makes no difference. It's just the probability of B. So probability of B is the same with and without that given information. Another way, if you want to think about it more mathematically, look at our formula up here. If A and B are independent, I could do probability of A times probability of B, and the B's cancel out, and we get A given B is just A. Okay, let's check out the rest of this page, and then we're going to start mixing up all these ideas in different orders for our remaining examples. So part A here, back to our familiar example, our baseball and home team winning. I'll use B for baseball, H for home team. Are they independent? Here it says answer with two methods, but typically one is sufficient. You don't need to show all three. If one formula gives you an answer, all the others are going to give you the same conclusion. But for practice, let's try it a couple of ways. So let's try it the way maybe you're most comfortable with, probability of B and H. I want to see, put a little question mark here, is that the same thing as B times H? Now remember, calculate these two sides separately and see if you get the same conclusion. So we've got our table, B and H, baseball and home team winning. So baseball and home team, there's 53 that meet that criteria. And be careful, there's no given information here, so the denominator is out of the overall total. 53 meet both criteria out of the overall total. So 53 out of our 490. Our right-hand side, baseball, we have 100 out of the overall total. And home team, we have 287 out of the overall total. And grab your calculators and pause if you want. Try and work out both sides here. And you should get that the left-hand side and the right-hand side are not exactly equal. So when the two sides are not equal, that means they're not independent. So I'll be looking for you guys to show your work in this way. Show the formula that you're checking, show the values that you're plugging in on either side, and then make your conclusion based on if the two sides are equal or not. Let's try one more just for example. So this is 2. Sorry, this is kind of illegible. This is supposed to be a method 1, method 2. So remember our formulas up here. We have the other two are conditional. So let's choose something, a conditional formula. So probability of baseball given home. I could have done home given baseball, doesn't matter. I want to see, is this equal to which one? Right, baseball. So it's like saying probability of baseball game is the same with or without that given information of home team. So let's work on finding the left-hand side here. Probability of baseball given home. So my given information is home, so what should the denominator be? Right, home team wins means I'm talking about just the 287 home team games. Baseball is my numerator there, 53 out of the 287. Then the right-hand side, probability of just randomly selecting a baseball game. Well, there's 100 baseball games, so I'll jot that down. And there's no given information on the right-hand side, so it's just out of the overall total. Baseball in general is 100 out of the 490. Again, if you work out these two fractions, you'll notice these guys are not equal to each other, close but not exactly equal. So when the left and right are not equal, they're not independent. I'm going to write the other word for that here, dependent. And you can use either phrase that you want. Dependent. Okay, so we can use all three formulas, test all three, and we're going to get the same conclusion with all of them. In future examples, you'll see that just trying one of these is sufficient. You don't need to go through all of them. All right, and then this last one, I just want to be really clear here about independence and disjoint. They do not mean the same thing. So up here, I also made that note here. So disjoint means the probability of A and B is equal to 0. The A and B cannot happen at the same time. There's no overlap, nothing in common. Whereas independence means that the A and B, the and or the overlap, is found by multiplying the two together. So they're saying two very different things. Make sure you're careful and don't get those switched around. So at the bottom here, our baseball and home team disjoint, we need to look at the probability of the and. And remember, disjoint is saying, is that overlap equal to 0? Can they both happen at the same time? Well, in our case, sure. We had several games that were both baseball and won by the home team. And specifically, we had 53 games out of all of our games. Remember, there's no given here, so the denominator is the overall total. So 53 were both baseball and won by the home team. So sure, it can happen. It does not have a probability of 0, so they are not disjoint events. And remember our terminology here, we also said mutually exclusive means the same thing. So they're not disjoint or not mutually exclusive. Okay, on the next video, we're going to start working through some examples where these are all mixed up in the question and work on using all of our probability tools that we have.